Chapter 12. Previous chapter, what we did is we learned how to solve equations that contain rational expressions. And so now that we've learned how to solve those equations, we can look at some word problems that will lead to setting up a rational expression equation. So before you can solve these types of problems, it makes sense, as we did in chapter 11, to learn how to solve those types of equations. And this chapter sort of builds us up somewhat slowly. We talk about rates, and obviously we have a couple definitions here on the first page, rate and a unit rate. And so we're going to be dealing with a lot of things like speeds, miles per hour. We're going to deal with things like unit rates. Okay, how, for instance, in terms of population, how many people live per square mile, live in a square mile area. So different things like that. Here are some examples of some rates that you could have, but basically what you're doing is comparing one quantity to another one. And as you notice with the rates, we see a non-unit number on the bottom in the denominator. So Game and Fish maybe captured some deer on a deer cam, or somehow estimated how many deer there are per 6 square miles. So ratio 42 deer per 6 square miles. A baseball statistic maybe 14 hits for every 38 times at bat. And one that we're going to probably run into first, 27 miles every 3 hours. We're going to work some problems that involve distance, rate, and time. And this last one here. So these are all examples of rates. Okay, fertilizer per acre. Now the only difference between these two, here we have unit rate, is that the denominator has a number 1 associated with it. So here we see 1 hour, 1 square mile. And so for perhaps a rate of pay, you get out of college, you make it through, you get your degree, maybe you'll get $12 per hour. I don't know. But this is an example of a unit rate. Okay, $12 per 1 hour, and 1 is our unit number. And this other one, of course, 16 people per 1 square mile. It's a unit rate because we're comparing it to 1 single mile, square mile, in the denominator. So maybe said a little bit too much about that. Not really too big of a deal. Definitions are pretty simple, but this is sort of the basic thing that we're going to be dealing with in this chapter. Rates and comparing one rate to another. Okay, this is just telling us what we need to do, the starred comment, if we want to change a regular rate to a unit rate. And so basically what happens here is if you go off to the side and you pick out your calculator, $7 per 5 pounds. Okay, and when you're reading this, you can just replace this big fraction bar division sign with per. Okay, because that's what it translates to. Now as for the 7 and the 5, if we want this to be a unit rate, then we want to turn the 5 into a 1. Okay, and they sort of walk you through how you would deal with the fractions, but basically what we end up doing is simply dividing 7 by 5, and you see we get a 1.4, and that's what our unit rate ends up being. 1.4 is dollars, and then that is per pound. Okay, the denominator is now 1 pound. So real simple. Just divide the two numbers and you'll get a unit rate. So example 1 says 8 pounds of bananas for $4.32. We would write that this way. Okay, and if we wanted to calculate the cost per pound and we wanted a unit rate per 1 pound, then we just simply divide 8 by 4.32. So we pull out our calculator and we say 8 divided by 4.32, and we get 1.85. I'll round it. 1.85 pounds, and then we can just associate 1 with the dollars on the bottom. If we were to write this in words, we would just simply say 1.85 pounds per dollar. So we're going to work a bunch of examples, just simple, straightforward application problems where there is only one rate. Okay. Later in the chapter, we're going to deal with problems that contain two different rates, and so that gets a little bit trickier. But first, we have to tackle, or at least get refresh our memory on how to deal with just one rate. Next page, we have example 2 here. It says Joe ran 2 miles in 40 minutes. So we got a couple questions. What is his rate in miles per minute? Okay. So whenever this word per is used, that just simply means that the first unit goes on the top and the second one goes on the bottom. So this is the way we're going to set up our ratio, miles per minute, or our rate, you could say. Alright, so 2 miles goes on top. So we have 2 miles per 40 minutes. Okay. This is his rate. Usually we want to convert that into a unit rate, and so we could take our calculator and just simply divide 40, or not 40, but 2 divided by 40, and we get 0.05 miles per minute. Okay, what was Joe's rate in miles per hour? Alright, this one we're going to have to do a little bit of a unit conversion. So here we write down our rate the same way we did in the previous problem. Minutes. Okay, and we already have miles per. Okay, miles is on top. We have our fraction, but now on the bottom we have hours, and what we needed to do is get rid of the minutes and replace it with hours. Now we have to, what we can do is multiply by a conversion factor here, and that's simply just going to be another fraction. Alright, if we want the minutes to cancel out, then we're going to go over here and we're going to put minutes on top of our conversion fraction, and then we just simply put the unit that we want on the bottom. And so what's going to happen with the units is just like the numbers and variables, they'll cancel out if they're equal. So minutes and minutes cancel, and now we just have hours left on the bottom. Now, now minutes to hours, we have our units set up right, but now we need to put the numbers along with our units that we put here in our conversion. So how do you convert minutes to hours? Well, 1 hour equals 60 minutes. Okay, so 1 goes with the hour, 60 goes with the minutes. The units of minutes canceled, and we multiply. We have 2 miles, and I'll just leave it mi for miles. And well, hold on, no, I should have multiplied 2 by 60. So 2 times 60, I get 120 miles. And then on the bottom, 40 times 1, I get 40. The minutes have been knocked out, and now I'm left with hours, HR. And 120 divided by 40 will give us an even 3. And so this would be miles per hour, mph. Okay, a simple formula as far as our rate, miles per hour, and then the time and distance. How are they related? Well, if we're traveling at a certain speed, and that's what you can think of when you read rate, and we maintain that speed for a certain amount of time, if we wanted to know how far we travel, we just multiply the two together. The speed times the time equals distance. In this case, we're going to continue to use rate instead of saying speed. Alright, so we're not just going to use this form of the formula. This one formula actually contains it's sort of a 3-in-1 deal. We can rearrange this with what we know about algebra and get 2 other formulas. So for instance, D equals RT. Perhaps we were given D and T and the rate was missing. Well, to find the rate, all we do is just divide both sides by our time, and we should see that the T's cancel on the left, and that R is just simply the distance divided by the time. Likewise, if we had a distance rate time problem, and say we were given the distance and the rate, and we wanted to solve for the time, well, that means we want to get time by itself. So in this instance, we would just divide both sides by the rate, R. On the right, the R's are going to cancel, and we find that T would equal the distance divided by the rate. Okay, so we have basically 1, 2, 3 formulas built into one. This is the only one that you really need to memorize. These other 2 can just be derived from using algebra. So just memorize D equals RT. Alright, so we're going to work a couple problems here where we apply this new formula that we've used. There is an example worked out here for you to read, but we have some that we're expected to work out ourselves. So I'll just skip to example 5, and it reads, on a trip to his favorite fishing spot, David Earl drove at an average speed of 60 miles an hour for 2.8 hours. How far did he drive? Okay, so how far is referring to D. Alright, so we want to figure out D, and this 60 is our rate. Okay, miles per hour. Whenever you see per, the number that's it's associated with is your rate. So R gets replaced with our 60. And that's kind of confusing the way I've wrote that. I got the arrow here. D is just simply what we're solving for. That was the purpose of the arrow. But 60 is our rate. And then 2.8, we have hours here. That's a time. So in the place of T in our formula, we put a 2.8. And nothing really complicated here. We just multiply these two together. And I'll pull out my calculator and type 60 times 2.8 to get 168 miles. Okay, I want to show you something with the units because I didn't use any units in combination with the 60 and the 2.8. But the rate was the 60. So if we just look at the units, then 60 was miles per hour. Okay, miles, big fraction bar, hours on the bottom. And we multiplied that by 2.8, which has the units of hours. So we multiplied by hours. Hours in the denominator, hours on the top of the other fraction. They cancel one another. And you can see that the only unit that we're left with would be miles. So, and we already knew that R times T is equal to a distance, and miles are a unit of distance. So, labeled the 168 with miles. Alright, so pretty straightforward, simple problems, just applying this formula, D equals RT. Alright, so example 6 says Ronnie averaged 65 miles per hour. That would be our rate. On a trip that took him 2 hours and 15 minutes, how far did Ronnie go on this trip? So again, we're asked how far, and so we're looking for D. And we do have our time, 2 hours and 15 minutes. But there's a problem. We do not want to mix units of time, and here we have hours and there we have minutes. So what we need to do is the 2 hours is fine. We need to convert these minutes to hours. So all we're going to do, minutes is on the top, and we're not going to fool around with this 2 hours. We're just going to take the 15 minutes, multiply it by 1 hour over 60 minutes. Okay, this minutes unit is in the numerator, and so to cancel it out, we put minutes in the denominator of our conversion fraction. They cancel, and we're left with hours on top, and 15 divided by 60 is a 1 over 4. If we convert that to a decimal, we get 0.25. So we just take this decimal part, go back over here and tack it on to our 2. So long story short, 2 hours and 15 minutes is the equivalent of 2.25 hours. Alright, our rate is associated with hours. That's what this H stands for here. And so we want to keep the 2 hours, but the 15 minutes caused us to have to do a little bit of extra work and convert to get only hours. So now that we have our numbers, 65 and 2.25, we go and let me pull my calculator over here so we can see it. We multiply 65 by 2.25. 0.25. Enter. 146.25. Okay, and we're looking for a distance D, and the only units of distance that we read about in this problem were miles. So our distance would be 146.25 miles. Okay, 7. It says Morton drove 320 miles in 5 hours. What was his average speed? So the question is, what is the speed? And so speed is a rate. That is our missing information. If you want to, really you can just write down D equals RT and put the numbers in there. In this case, we're missing the R, so R is going to go down on the next line, and our T, here we have hours, so 5 replaces the T, and then we were given the distance this time, 320 miles. Okay, notice it doesn't say miles per hour, so this is not a rate. It's just straight miles, and the 320 replaces the D. So we want to solve for the rate. To do that, the 5 is multiplying the R, so we do the opposite and divide. 5's cancel. And let's see, what do we get? We get 5 goes into 32 6 times, and then we're left with a 20, 64. Okay, the units in this case, what we have over here on the left is the 320. The units of that number were miles, and the units of the 5 were hours. So 64 does end up in units of miles per hour. Okay, example 8. How long did it take Jimmy Mack to run 1,760 yards if he were running at the rate of 220 yards per minute? So our distant units, they're the same, yards and yards, and now we're dealing with minutes, and that's okay. So but still we set up our formula, D equals RT. We can use the same formula. It doesn't matter what the units are. We just want the units to be consistent. So he's running a distance, and that would be this figure here, 1760. And again, we're missing, well, no, we're here, in this case we're given the rate. Okay, because the thing that should tip you off with the rate is this keyword per. So yards per minute. 220 replaces the R. Okay, and so we're looking for the T. It said how long. Alright, and again, you want to make sure that your rate contains the same distance units that the actual distance has. Okay, you don't want to mix units. So to solve this, we divide both sides by 220. We whip out our calculator and we type 1760 divided by 220, and we get 8. 220's canceled, and all we're left with is a T on the left. So the only unit of time that we read about in this problem was minutes, so this would be 8 minutes. Okay. Alright, so now that we have a little bit of practice and a bit of a refresher on how to work with rates and whatnot, and we've learned a new formula, distance equals the rate times the time, we're going to look at what we need to do in order to handle an application problem that involves two rates, or for instance two things that are traveling at different speeds, maybe different directions, and they travel for a different amount of time. What we do, which these first two or sort of general steps that you can use for any word problem, not just these type. But step one is to read the problem. Okay, try to get, and you may have to read it several times to just try to maybe work out what the problem's asking, what information's given, sort of imagine the scenario that the problem describes. Step two, try to write out what variables that are unknown, as far as, and that usually, good place to look for that would be the question. Okay, so you're going to use variables and whatnot for unknown quantities, and sometimes we have formulas like DRT, and so there's variables that you probably need to define. And that leads to step three, which you're going to see quite a bit of this throughout the course of the next couple pages. We lay out a table. Okay, it is a, I guess you could say, a 4 by 3 table, where we just have 3 columns that we use and then the 2 rows underneath. So this cell here doesn't really get used. So for instance, just to give you an idea as to how we're going to use this, for instance, say we had 2 trains traveling at the same time. One would have one rate, one would have a different rate. Maybe we could call it R2. Okay, R1 for the rate of train 1. They could be different, and they could travel for maybe the same amount of time. And then according to R, T, and D, our columns, they have a relationship. In other words, we can multiply the first 2 columns, R and T, to get this third column, D. So D1 would just simply equal R1 times the time that it traveled, R1x. And then for train 2, maybe it travels and covers a different distance than train 1. So we could write D2 equals R2 times X. Okay, so these problems are sometimes going to work out differently. I just wanted to give you an idea as to how we're going to use this table. Okay. Step 4 is sort of specific to these DRT type problems. A lot of times what ends up happening is we're just given the numbers for one of the columns. We use expressions to fill out a second column, and then we multiply or divide the 2 columns that we have to get the third missing column. And that's all I'm going to tell you right now, because soon enough we'll be working our own problem, and you'll see what I'm talking about. Step 5, typically that third cell that you calculated in the table is where you're going to derive your equation. And then to finish the problem, step 6, you simply solve the equation for your variable, and hopefully that gives you the answer. Alright, next page, they show us a word problem up here at the top, and our first step is to just simply read it. It says Pat and her cousin David left Pat's home at the same time. Pat drove north 55 miles an hour. David drove south at a rate of 60 miles an hour. How long did they drive before they were 230 miles apart? Okay, it doesn't hurt to maybe draw a little picture off to the side. So I just put a star, and they're driving from home. And Pat, let's see, she takes off north, so I'm going to draw an arrow upwards, and I'm going to label it 55 miles an hour. And then David, he goes south, and he's traveling a little bit faster than Pat, so maybe you could make this arrow longer. And I'm going to label that arrow 60 miles an hour. Now, it says they leave the same time and whatnot, but one thing to notice about the distance that we were given is that it says they were 230 miles apart. It didn't say that one drove 230 or the other one drove 230. This is sort of their combined distance. So with this little picture, you should see that the distance is from the tip of this top arrow all the way down to the tip of the arrow that heads south. So this is our distance here. Okay, it's the combined distance of Pat and David. Alright, so step one, and you can, if you look at our table, you can see that they pretty much already filled it out. In the rate column, we have 55 miles an hour for Pat, 60 for David. They left the house at the same time. Okay, now one travels farther than the other one because one's going faster. But if they left at the same time and we stop them after a certain point, then they will have traveled the same amount of time. Now, this is supposed to be assumed once you read this phrase right up here in the word problem. If they left at the same time, then their times are typically going to be equal. So, and we don't know the time. So that's how we use our variable here. They put in the T column X for both Pat and David. They have different speeds, 55, 60, and so the R and the T are the columns that we filled out first. And you see here that for the distance column, the third one, we just simply multiplied the first two together, 55 times X, and here you see 55X, and then for the next row we have 60X. Okay, so here we define, just write out in words what X represents. It's the time that they drove before they were 230 miles apart. Okay, what is equal to what in the problem? Well, we've already talked about the distance, and this 230 that they gave us is just the distance of Pat plus the distance of David and their combined distance. So we have addition in between. You add the two together and that equals 230. So our equation that solved the problem came from this third column here that we had to calculate based on the other two columns. Okay, so step 3, we write out our equation, replacing distance of Pat and distance of David with 55X and 60X. We get our X by itself, and there we have the answer. They go into a step 4 here and they check it, and they basically just go back to the table and replace the X with a 2 and then compare all of the different numbers together. So this is the distance Pat drove and this is the distance David drove. One's going faster, so you would expect David to drive farther, and he did 120 miles, Pat did 110. So that sort of checks out and makes sense. And then the two distances even add back together down here at the bottom of the page to give us the 230 back. Okay, so that gives us seeing an example gives us a little bit better idea about solving these problems. But to really learn, we need to work our own. So example 9, we read the problem. Shirley and Nelda are on 2 trains that leave their respective stations at the same time, headed towards each other. Shirley's train averages 85 miles an hour on the trip, If the two train stations are 372 miles apart, how long will it take the two trains to meet? Do not do any rounding. So I'll draw a little picture like I drew in the last problem. And we'll say that this is Shirley Station. And then up here on the top is Nelda's. And it says that Shirley averages 85 miles an hour. Oh. And Nelda is 70, a little bit slower. So maybe draw this arrow down. And then it tells us that the two stations, which my stars represent my stations, they are 372 miles apart, and Shirley and Nelda are headed towards one another. So over to the side I'll draw a dimension, and I'll label this with 372. Okay, now if we drew this proportionally, this was 85, this is 70, which this probably should be a little bit longer. If this is 85, this should be almost as long as that, and it looks closer to half. But if we drew this picture proportionately, then we could just simply estimate how long this is going to take. And also at the same time, this 372 was proportional to the 85 and the 70. Then we could just simply double Shirley. Okay, this, for instance, this first arrow would just simply represent the first hour. The red arrow would represent the second hour. And likewise, we want to go up here and double this arrow. So this is how close they would be after 2 hours. And then we could go back and draw another arrow. And so if another hour passes, this is how far Shirley would travel, third hour. But then during that hour, Nelda would travel also. So we draw another arrow just as long as these first two up at the top. And so what we see, if this was proportional, what we see is that they pass each other. So according to this picture, which these should probably be further apart, but according to this picture, they meet somewhere between the second and the third hour. Alright. Now, that is not entirely necessary. You especially don't want to do that if you're going to burn up any kind of significant amount of time. What we want to do, or put most of our time into, is our table. So we write out RTD, okay, because this is the formula that we need to apply to each train. And then in our rows, okay, we have 1, 2 rows. We'll write Shirley's train, and then we'll write Nelda's train. Okay, so all the information about Nelda will go in this second row right here, and then all the information about Shirley's train will go in the first row. Alright, so we were given 2 rates, one for each train, so we'll put that into our column. And so they just give us the number for the R column. 85 goes here, and then 70 goes right there. Now, they're headed towards each other, and they leave the station at the same time. Now, Shirley is going to cover more distance than Nelda, and so maybe they meet right here, a little closer to Nelda's station than Shirley's. But when they reach this point, they will have traveled the same amount of time. So in the t column, we put x's here. Okay, and so at some point when you're filling out your table, one of the columns you're just going to have the numbers, and then the second column you typically have to use a variable to complete. And here in step 1, we're told that we want to define this variable, and we're going to call it the time that it takes Nelda and Shirley to meet. Okay. Now for the distance, notice that we're not going to put 372 here or here. Alright, this 372 miles is traveled by both Shirley and Nelda, so we can't put it in one row or the other. So what we're going to do instead is say, well, we can calculate D because we know the R and the T. Alright, our columns are based off of the formula D equals RT. So we can take what's in the rate column and the time column, multiply it together, and at least get an expression for the distance. And we do the same thing for Nelda, and we get a 70x. And at this point we've completed the table. Alright, what is equal to what in this problem? Well, we have Shirley's distance, we have Nelda's distance, and then after you've completed the table, typically what you do is you look back at the problem up above and you spot a number that you haven't used in the table. So we had just talked about how this is our total distance that they travel together. So what we would say is we'd write Shirley's distance, if we wanted to write it in words, Shirley's distance combined with Nelda's distance is going to equal the total distance, which is the 372. Okay. Nelda's distance is right here in the D column. It's 70x. And then Shirley's is 85x. So here we have, if we bring the equal sign down, here we have the equation that we need to solve the problem. Alright, so write an equation and use it to solve the problem. We have 80x plus, hold on, let me go check my numbers. We have 85, sorry. We have 85x and 70x, and that equals 372. Alright, simple equation. This is an x term, that's an x term, so they add together to give me 155x. That equals 372. And to solve for x, just takes one more step. We divide both sides by 155. On the right, we have to divide 372 by the 155, and we get 2.4. Okay. Now you may have to go back where you defined your variable to realize what units this number has. Okay, x is how long it takes Shirley and Nelda to meet. So the units of time that we were given in the problem was hours. So this is 2.4 hours. Alright, if you wanted to check the answer, I would just simply take the equation and go back and plug in the 2.4, the number you found, for x, and make sure that it works out to give you 372. Alright, so more calculator work. 85 times 2.4 gives me 204, and then 70 times 2.4 gives me 168. Okay, we add that together, and we do get 372. Checks out. Alright, so that was just our first problem. That is definitely not enough to really get the hang of these DRT problems. So, of course, on the next page, we work another one. And there's really no cure for being weak at solving application problems other than just working as many as you can stomach. Okay, and that's what ALEKS is for. And you know, there's also problems at the back of the chapter, so don't shy away from a little extra work. The more problems that you work, the more this is going to make sense. So, example 10, it says Bub started out one morning walking at the rate of 2.5 miles per hour. 30 minutes after Bub left, his friend Ed Winston showed up and started walking on the same path, but at 3 miles an hour. How much time did it take Ed Winston to catch up with Bub? Okay, so here I am going to draw a star, and this is basically the starting point. And these two guys are walking along a trail, and I'm just going to write that with a dotted line, and we're not worried about where this trail ends. Okay, so Bub starts out 2.5. He's going kind of slow, so I put a small arrow there. And on the other side, what I'm going to do is I'm going to write a slightly longer arrow for Ed Winston, his friend. Now, it says that they do not start at the same time. So what happens is Bub, let me go ahead and label this left side Bub, and then this other side Ed. Bub starts out, and he is going to travel, if he's going 2.5 miles per hour, in 1 more hour, 2 hours, he will be this far along. In 3 hours, he will be that far along. 4 hours, there. Okay, so we just copy down this arrow 4 or 5 times, however far you want to go out. And now we'll go back and we'll look at Ed. Well, this will be, and we'll talk about Ed's first hour. So this is his first hour. He will have traveled 3 miles. Okay. If another hour goes by, then we'll double Ed's distance. We'll double the arrow here. So this would be the second hour. And so 3 plus 3 would be a total distance of 6 miles. Now, if Ed travels for 1 more hour, then you see in only traveling 3 hours, he's passed Bub. Bub has only been traveling, or he's been traveling for 4 hours, but he's only went this far. And here, this third arrow of Ed's overtakes Bub's. So based off of our picture, maybe we could say, which we didn't draw this accurately, so you can't really go by the picture, but if you were going to take this for face value, then we would say that Ed is going to pass Bub between the second and third hour. Okay. Now, here's our table. Again, we have R, T, and D. And so on one row, we'll put Bub, and then on the other, we'll put Ed. Okay. We want to know when they're going to meet. So here we go back to the problem and pick out what all we know about the problem as far as rate, time, and distance. We've got numbers 2.5 for Bub, that's his rate, and then 3 for Ed. So one of the columns, we're just given the numbers outright. Now this second column, time, is the one where we're going to have to use variables to nail down. Alright, so in this case we say that Bub started out one morning. 30 minutes after Bub left, his friend shows up. Okay, we're going to call X the amount of time and we're only going to put X by itself in the T column, Bub's row. We're going to call X the amount of time that Bub travels before he is passed by Ed. Okay. Now, if Bub has traveled X hours, then according to Bub, Ed started 30 minutes later. And so by the time they meet, the time that Ed walked will be a half hour less than the time that Bub traveled. So X minus a half. Okay, so we were just given the numbers for one column. We had to nail down a variable to complete the second column. And in this case, the X's aren't the same. The times aren't the same because one started later than the other one. Alright. But the procedure is still similar to the previous problem. We have R, we have T, and now we can calculate the distance. Or at least write an expression that represents the distance of both Bub and Ed. So this first distance is 2.5 times X, and then this second distance of Ed is X minus a half. Okay, notice that I didn't put 30 here for the half. Okay, we want to base our problem on hours. Okay, 3 is in terms of miles per hour. 2.5, it's in terms of miles per hour. We don't want to switch our units for time in our T column. So I want X to be in terms of hours, and so instead of putting 30 here, I put half because 30 minutes is a half hour. Alright, and Ed's time is shorter, so we subtracted a half. Okay, what is equal to what in this problem? Well, when I first started out, I drew a picture, and the two guys were walking along the trail, and we said at some point as the hours go by, Bub is going to get passed by Ed. And so what we mean by passed is that they have traveled the same amount of distance. Alright, if they travel the same amount of distance, then the way we set up our equation is we say the distance of Ed equals the distance of Bub. Alright. Their two distances are equal. One passed the other and they took off from the same spot. So here we write 2.5x equals 3 times x minus a half. Alright, we would distribute the 3. Half of 3 is 1.5. We get the x's on the same side, so I could subtract 3x from both sides, and I'd get a minus 0.5x equals 1.5, and that's a negative 1.5. And now to finally get x by itself, I divide by negative 0.5 on both sides, and I get x equals 3, and our time units are hours. Okay, to check this problem, one thing you could do is you could go back to the table and just plug in x anywhere that you see one, and calculate all of the missing information. I am simply just going to plug it back into my formula and make sure the left hand side equals the right hand side. Alright, so x is replaced with 3, and 3 times 2.5 would be 6, plus a 1.5, 7.5, and then 3 times, okay, inside the parentheses we have 3 minus a half, so that would be 2.5. And so yeah, that is that's also 7.5, and so the two sides equal, and our solution of 3 hours checks out. Alright, example 11. Dave Jimerson drove the first third of his trip at an average speed of 40 miles an hour. He suddenly realized that he would not arrive at his destination unless he sped up. He drove the remainder of his trip averaging 60 miles an hour and arrived 7 hours after he started his trip. How many miles did Dave drive? Okay. So what we're going to do here, we've been given some numbers, and we don't have two different people or two different trains or anything like that. We have one guy, but his trip is broken up into two parts, so that's what's going to label our two rows. So we'll label this first row as first part of trip, and then this other one the second part. Okay, so it says the first part he traveled 40 miles an hour, and the second part he drove 60 miles an hour. He sped up a little bit. Now it says the first third, and so kind of subtle, but this should tip you off as to how we're going to set up the distance. And up until this point, what we usually been doing is we write the numbers into the row column, and then we would use our variable for t. But in this case, we're given more information about our distance than the time. The 7 hours can't be used in the T column because this is the total time for his trip, and we don't know how that's divided up between the two parts. So we'll use this as our total, and what we'll do at this point is we'll use our variable to construct our D column. Now our X in this problem is going to represent the total trip, the distance of the total trip. So if I use that for my total distance, then up here for the first part, then I can say, I can use this phrase that was in the first sentence. First part of his trip was a third of his trip. So I'll simply write in the D column for the first part, 1/3 times the total distance x. And so if the first part was a third, then that only leaves 2/3 for the second part. So for in the second row, D column, we write 2/3 x. Now, what I'm going to do is I'm going to calculate the T column based off of the R and the D. So, as we did before in the first part of the chapter, this is the formula that you should have memorized, D equals RT. And to solve for T, what we do is we divide both sides of this formula by R. R cancels, and we see that to calculate the time, we divide the distance by the R. Okay, so what we're going to have in the T column is 1/3 x divided by 40. And then for the second row, we're going to have 2/3 x divided by 60. Alright, there's a number typically that is left over in the problem that was not used in the table, and in this case that number is 7 hours, and it refers to the total time. There's two ways to calculate the time in this problem. We can add time of first part of the trip to the time of the second part. Well, there's not two ways to calculate it, but on one hand we know the total time, it's 7, and then on the other hand we have expressions for the two individual times. So the time of the first part of the trip plus the time of the second part of the trip, which is in our table, should be set equal to 7. Alright, so now that we have our table completed and we have our formula written out, we will set up our equation using the expressions and the numbers, or basically just the T column that we have here. This third calculated column is the one that you're going to use to construct your equation. So I'm going to go down to part 3 and write out my equation, which is 1/3 x divided by 40 plus 2/3 x divided by 60, and that has to equal our total time. So this formula here is time 1 plus time 2 equals time total. Two times add together to give us the total time. That is the structure of this equation that we've come up with. Now, our goal is to find this x. So, sort of weird looking because we have a fraction on top of the 40 and the 60. So, what we're going to do is rearrange this. And to do that, one thing we could do is remember what we learned from chapter 11. We could multiply the whole equation by lowest common denominator to get rid of this 40 and this 60. Okay, so smallest number that 40 and 60 will divide into is, let me think up. That would be 120. So 40 divides 120 and we get a 3. Okay, so the 40 gets knocked out and what we have left is what's on top of the fraction. Now the 120 is going to multiply the second fraction, so we say 60 divides into 120 2 times. So the 60 gets knocked out, we've divided it into the 120, and now we get what's left on the top times the 2. And last but not least, don't forget to multiply the 7 by the 120 also. We end up with 700 plus 140, 840. Alright, so still we need to go back and clean this up a little bit. This 3 knocks out the 3 on the bottom of the 1/3 and just leaves us with an x. This 3 doesn't cancel. We have a 4 over 3x. And then we have the 840 on the right hand side. So we still have a fraction left. Maybe we should have left it 3 over 3. That probably, we'll go back and put that in here. Instead of canceling these 3's out, we'll leave it 3 over 3 so that the denominators are the same. And we'll add these. This may be the quickest way to work this equation. 3 over 3 plus 4 over 3 would give us 3 plus 4, 7 over 3x. To get the x by itself, we multiply by 3 on both sides. 3 times 1, or 3 times 80, that gives us 2400, and then 3 times 40 would give us a 120. So we end up with 2520. Finally, we divide by 7. And we get 3. 7 goes into 25 3 times, and then a 420 is left, and so we get 360. Alright, what was our x? Our x was, let's see, our x was the total distance of the trip, so this would be 360 miles. Alright, so the first part of the trip, D first, it said that in the first part he drove a third, so that would be 1/3 of 360, 120. How long was the second part of the trip? It was 2/3 times 360, which is 240. And then we could also go back and we could figure out the times, but I'll leave that to you. Okay, so this is kind of a long chapter, and this hour is this video is a little over an hour, so I'm gonna stop it here and finish the rest of the chapter in a second video. Thanks for watching.